Okay, well, hello everyone, and welcome to Inside Akira Ransomware's Rust experiment. My name is Ben, I'm a security researcher, and before we get to today's story, I'm going to start with the prequel. About 2 years ago, I got interested in the question of what Rust binaries actually look like on the inside, so I took basically every feature of the Rust programming language and ran them all through the compiler and reverse engineered all the assembly code that resulted. This was nice for understanding how these binaries were built, like generally, but then what do you do when you run into an actual malicious Rust binary in the wild, outside of laboratory conditions? It's probably highly optimized, it's probably compiled in release mode, and this is like a notoriously difficult issue. And there's been some efforts during the past few years to improve the automatic tooling on this front, but I have to say that currently in the year 2025, reverse engineering Rust binaries is really far from solved problems still. The reason for this boils down to, if I may use an analogy, if you want to build a really great automatic pizza maker, you should first have the manual baking of the pizza down to a precise science. And by analogy, if you want to automate away all of the sorrows and difficulties of reverse engineering Rust binaries, you should probably have reverse engineering Rust binaries manually down to an exact science first as well. But how often have you seen this actually done? I mean, someone taking a malicious, highly optimized Rust binary in the wild and just doing an old school full RE of it, the way we used to do with C binaries all the time. Very few people want to do it, so we decided we were going to do it. And soon enough, opportunity knocked. Akira Group released a Rust version of their encryptor. So we took this binary and reverse engineered the entire thing from beginning to end, resulting in a rather exhausting report, which is available in a blog post of the same name as this talk. We're not going over the whole report today, we're just going over 3 highlights where an unusual insight was required in order to break through an obstacle and allow the investigation to continue. But first, we can do this without a short word about who these Akira people are. They are a RaaS group. They've been with us since at least as early as 2023. They've attacked hundreds of organizations in the US, in the EU, in Australia. They've caused dozens of millions of dollars in damages. They like to attack exposed VPNs using 0 days, 1 days, and credential stuffing, and they like their cross-platform malware, which is presumably part of the reason that made Rust language attractive to them. Sure enough, around early 2024, they released the binary I spoke about earlier, and we got our hands on it. And the moment we did, several things immediately jumped out at us. First of all, this was clearly an optimized release build. None of the metadata that you usually see in a debug build, even if you run a simple obj dump, appeared in this binary. But more importantly than that, the execution chain for this malware was kind of weird. You have the main function, okay, which calls something named default action, which calls lock, which I guess makes sense for ransomware, which then finally calls something named lock closure. Okay, we are intrigued. Now, the thing is, usually at this stage of a research, what you're going to do is pose some very specific research questions. So you would be able to dive into the binary, fish out the answers you're interested in, and then pull back out. But now we were here in order to reverse engineer the entire binary. So we were reduced to the very newbiest techniques of reverse engineering, of going to the main function and starting reading the instructions one by one. And soon enough after starting doing that, we became confused. We ran into a bunch of these opaque function calls, and then there was this huge object with tons of fields. We had no idea what any of them were for. And this object was constructed and passed as an argument to this next function in the execution chain, default action. And the thing is that this malware only has one possible control flow. So this isn't a default action. It's more of an only action. We became suspicious. So we ran a web search, and we found what we suspected we would find, which is that the Akira devs copy-pasted a bunch of code from the README of a third-party Rust crate, specifically a Rust crate named Seahorse. This is a framework for creating CLI applications in Rust. And after copy-pasting this code, the Akira devs made as few modifications to it as they could possibly get away with, so that the result would still kind of perform the action they wanted it to perform. The result of this workflow was several vestigial remnants of the original boilerplate inside of the ransomware code, such as, for example, this strange string CLI bracket name, and the function name default action, which was just some kind of innocent placeholder, which somehow found its way into this ransomware. Now, armed with this insight, we could go back to all of those oblique function calls from earlier and realize that actually all of these repeated calls were just initializing seahorse flag objects. And we could go back to the huge object that we saw before and realize this was just an app object, again, from the seahorse library. And we could match all the field initializations line for line for assembly, from assembly to source, including naming all of the fields and realizing that, for example, this strange string CLI args, it goes in the usage field, and you even have a version string ostensibly showing the date on which this unholy binary was compiled. Now, to sum up this warm-up, we took what could have been 2 or 3 days of really painful reverse engineering, and we boiled them down into one educated guess. And I know what you're thinking. Yes, we ended up with all the information we could possibly want about how this main function operates, but nearly no hard work went into achieving that state of affairs. So what kind of reverse engineering is this? And my answer to that is that, personally, it's my favorite kind of reverse engineering to pull that off. So with that in mind, we're moving on to the main course, the default action function. And at first, we thought we were going to have an easy time with this function, because just like with the main function, originally, the Akira devs copy-pasted a bunch of boilerplate code from the README file of a third-party crate, this time from the crate indicative. This is a crate for creating colorful eye candy progress bars in the terminal. And we thought we were going to have an easy time just like with the main function. We're just going to look at the boilerplate they copy-pasted and match it line for line, the source to the assembly, and be done. But unfortunately, reality was not so accommodating to our fantasy. When you look at this function, default action, in the assembly level, you're going to see that, first of all, its basic block structure is not so pretty. And second of all, if you start at the top and begin reading, you're going to very soon see some stuff, like, for example, direct calls to the CFFI, which, strictly speaking, should not be there. And then you're going to encounter what I'd like to call the final boss of basic blocks. This thing is comprised of over 200 instructions, all of which operate on XMM words, and none of which I can pronounce. Now, usually at this point, this is where we would have scurried back and tried some sort of other approach, a workaround, such as using a debugger or maybe a sandbox. But we are now in the current era of technology, and there is a new thing that we can do. Brace yourselves, you all know what is coming. We delegated the task of understanding what this basic block does to our esteemed colleague OpenAI 03. This was before GPT-5 thinking. And OpenAI 03 chewed through all of these instructions, and when it was done, first of all, it hated us. And second of all, it came up with the correct answer, which is that this basic block was an elaborate dance meant to count the number of cores available to the current process for the sake of parallel computation. This was great, except this functionality was nowhere to be found in the actual sources that the Akira devs copy-pasted. And at this point, we had no choice. We had to sit down and, God forbid, do some thinking. And eventually, we hit upon a theory. If you look at the original boilerplate that the Akira devs copy-pasted, there's a piece of logic there that spawns 4 worker threads, exactly 4, a hard-coded number. And we figured that one of the Akira devs must have seen this and said, okay, this is nice for a README file, but it's not fit for production. So they switched out the hard-coded number 4, and they replaced it with a value that the user, the person invoking the binary, was going to supply via the CLI. But now what if the user doesn't supply a number of threads to spawn? Now you need the same default. So what's the same default in this case? Well, how many cores does the machine have? Which you would answer by calling the function available parallelism, resulting in the source code on the bottom. Now I want to emphasize something about the source code on the bottom. This source code is obviously not inside the Akira binary. This source code is not in the boilerplates that the Akira devs copy-pasted from indicative either. We are right now inside the Akira devs' head, reverse engineering their thoughts and deducing what source they must have written in order to implement the functionality that we reason they probably wanted to implement. So Armed with this foothold, we went to the function available parallelism and began digging down the call stack. Now, available parallelism calls a function named quota, which calls either one of two functions, quota v1 or quota v2, which calls a libc function named CPU count, which calls another function named CPU count s, which iterates in a loop, with each iteration calling some function named count ones, which finally calls popcount64, which is an LLVM intrinsic, which kind of sort of performs the logic that we talked about earlier of counting the number of available cores, but there's still some way to go from here to there. How do you get from a shortish LLVM intrinsic that lives 5 levels deep inside library code to this huge basic block that appeared in the same visual layer as the original dev offered code, and we saw the moment we started reverse engineering the default action function. But now when you pose the question like that, the answer is within reach, and it breaks down into two components, which are inlining and loop unrolling. The RaaS compiler took every call I just discussed, including available parallelism, calls quota, calls either one of quota v1 or quota v2, calls CPU count, and squished all of them into the same visual layer as the original dev offered code. We've taken the liberty of going through the entire basic block graph of default action and color coding all of them so you can get this like Christmas tree display of how all of those blocks, each belonging to different functions in different levels of the call hierarchy, are just like hanging out, chilling next to one another in a way that they have no logical right to do. If you scroll further down, you're going to find the actual final boss of basic blocks that I discussed earlier, which again, it comes from the intrinsic CPU count, pushed 5 levels up from its original position in the call hierarchy. And if you'll recall, there were repeated iterated calls to it, so the compiler unrolled this loop, resulting in the basic block as we found it. And the heartbreaking thing is that the Akira dev who wrote this code didn't even mean to write anything obfuscated. They just needed a feature. So they wrote down 2 words, available parallelism, thus setting in motion the series of events that culminating in us encountering this soup of basic blocks and that unreadable final boss of basic blocks. And this should give you some idea of what maybe makes Rust appealing to modern developers, because apparently you don't need a packer or an obfuscator. You just program normally and the obfuscation happens on its own. So the final highlight I wanted to talk about today has to do with what happens in the lock function. Now, despite its name, the lock function doesn't actually perform any file encryption. It delegates that task to a bunch of worker threads. But if you go and try to see how the control flow gets transferred from the lock function to one of the worker threads, first of all, you're going to run into the same soup of basic blocks from various levels of the call hierarchy. Fine, we're already used to that. But even at the tail end of the soup of basic blocks, you're going to see a call to some function named thread scope new. And as an argument, this function takes some oblique pointer, and the original entry point that the thread is supposed to begin its execution at is not to be found anywhere. Now, as a reverse engineer, nothing makes me more nervous than not being able to understand how the control flow even proceeds from point A to point B. So we decided that we were going to have to understand everything that's going on here, including the basic block soup and the oblique call to thread scope new. And the sad thing is that in a sane universe, everything I'm about to say right now would have been relegated to some separate course named RaaS Standard Library Internals. But the compiler has helpfully taken all of those internals and externalized them for us so that we have to reverse engineer them if you want to understand what's going on with the control flow here. And in order to do that, we had to do the unthinkable. We had to read the docs. Even worse, there were some parts where there were no docs, and we needed to read the RaaS standard library source code directly, which I can assure you was very fun. So fortunately, we at least have a leg up. We know that the Akira devs copy-pasted a bunch of indicative boilerplate code, specifically the code you see here. This code calls a library function named thread scope spawn. This is the function that generates the worker thread. And as an argument, this function takes another function, which is what the worker thread is going to execute. Now, in the original boilerplate, the thing you see in the yellow rectangle, this was just some harmless code. And of course, the Akira devs switched that out and replaced it with their own malicious logic that performs file encryption. So originally, this function, in its harmless form, it was a closure. And then it was replaced with something that performs locking. So at least that's one mystery solved of where we got the strange name lock closure. But that still doesn't answer our original question about how the control flow works. We needed to start our separate investigation of that matter. So we decided to start that investigation at the tail end of the basic block soup you saw earlier, at the call to thread scope new. This function takes two parameters. One is the stack size, and the other is some object of a type box dyn fn1s. This isn't intro to Rust. I'm not going to go over each one of those words and explain what it means. I'm just going to say that a box dyn fn1s is basically some struct with a vtable, the type of which is only going to be known at runtime, a construction I'm sure you've encountered in your dealings with C++. Specifically, fn1s is an interface, or as we say in Rust, a trait, that this object has to implement. This under the hood is done by having some function in its vtable that is going to call. fn1s means there's a function this object can call. So under the hood is going to be a vtable with a pointer in it implementing this function, so then the object can say, I'm an fn1, so I can be used as an argument for this function. But as I've just explained, box dyn fn1s is not a concrete type. It's more of a bound or a contract. We can't look at this and understand what the actual underlying concrete type is going to be when it gets passed to this function, or how it's constructed and where the original entry point of the thread is going to live, and so forth and so on. In order to do that, we need to look at the actual concrete type as it gets assembled. And in order to do that, we had to go all the way back up to the top of the basic block soup to the copy-pasted call to thread scope spawn. Now, thread scope spawn initializes some object named the builder. Spoiler, that's what gets passed to thread scope new. Builder has two fields, name and stack size, and it has a function implemented for it named spawn. Spawn calls spawn unchecked, and spawn unchecked calls spawn unchecked underscore. Now, spawn unchecked underscore is what actually constructs that entry in the vtable that allows the vtable to be fn1s compliant. It constructs the function that the object is going to call when finally someone comes to that object and says, hey, you're an fn1, so call your function. This is the source of spawn unchecked underscore. Basically, it takes the original naked entry point of the thread f and wraps it in a bunch of bookkeeping logic. You're welcome to try and look for the original variable f which contains the entry point if you're so inclined. Compile this, and you get that. This is the version in this assembly. Again, there's a whole bunch of bookkeeping around it, and highlighted in green, there's the naked call to the original entry point. And this is the vtable, including the destructor, and finally there's the vtable entry, which points to what you just saw previously on this slide. So this means that the original entry point the thread is going to begin its execution at is, let's take a deep breath, inside of a call instruction, inside of the shim, pointed at by a vtable entry, where the vtable is constructed by a library function, which got called by a library function, which got invoked by a builder object, which was initialized by the original library function thread scope spawn that the Akira devs copy-pasted from the indicative sources, or the README files to be more exact. And the Rust compiler took everything that I have just described and inlined it all into the same visual layer as the original dev effort code in the log function for us to see and appreciate and have to reverse engineer if we want to have any hope of understanding how the control flow works here, which we did. So thanks for the experience, Rust compiler. Now, in conclusion, if you look at the theory, you're going to get the idea that the worst part of dealing with reverse engineering Rust binaries is dealing with the trait system and everything downstream from that. And that is partially true, but if this practical experience has taught us anything, it's that aggressive inlining of library code is no less of a hassle to deal with. Now, one of these days, maybe we're going to get an automatic tool that can look at a function and basically extract a basic block subgraph from it, point at it, and say, that's a library function, and I can name it. Maybe we can even get a tool that can do this recursively 5 levels deep, as was clearly required here. But until that magical day happens, it pays off to know about this stuff. I can tell you from personal experience that some months After dealing with Akira, I got handed another malicious Rust binary to reverse engineer, this time a ransomware, a binary having to do with the funcsec ransomware. And I had a much more tolerable time with it because I had already worked through all of my initial shell shock and confusion when working on Akira originally. So hopefully I've been able to take that benefit and impart at least some of it upon all of you today. Thank you very much for listening.